Okay, let's talk through this. So, we can combine these equations, and we can take what we know for force due to gravity and we can plug it in. So we can say this is the mass of the object times by the acceleration due to gravity, which is g, m of the object, the mass of the Earth, over r squared, okay? Which r is the radius of the Earth. So let's just quickly address that. If this is the Earth, an object on the Earth is unbelievably tiny in comparison, right? And so if we're going to take the radius from the center of the Earth to the outside of the Earth, do you see how it's really not any different than taking it from the center to the center of mass of the object? So we can use r of the radius as the r component from the center of mass of one object to the center of mass of the other. Okay. Now, I like to get this all on like one line. So I'm going to multiply both sides by that r squared. So what we end up with is r squared m1 acceleration is g m1 mass of the Earth. And look, m1 is on both sides of the equation. So that cancels. And so what we're left with is r squared acceleration due to gravity g and mass of the Earth. And we're solving for the mass of the Earth. And so we'll divide by g. And so mass of the Earth is equal to r squared times by acceleration due to gravity divided by g. Now it's interesting. You have to be careful when we're plugging all this into our calculator. Okay, so let me show you how I would do it. So r squared. So here's going to be the top of my fraction, and I'm going to take the radius, 6.38 times by 10 to the 6th, but this whole thing I'm squaring. Okay. I think it's unnecessary, but I think we could put another parentheses in there. And then times by the acceleration due to gravity, 9.81. And then this whole top component is going to be divided by the g factor there. And so I'm going to plug in 6.67 times by 10 to the negative 11. And notice I put it in parentheses because I want to keep that whole component together. I'm dividing by the whole thing, not just by the 6.67. Okay, and we get, let's see, working with 3 sig figs, so we get a final answer of 5.99 times 10 to the 24 kilograms. Times 10 to the 24, that's huge. So really think of how massive the Earth is. And if you have some time, go compare it. Like just Google mass of the Earth in kilograms, and it's really amazing how close that value actually is. Okay, now let's talk about weightlessness. We addressed this concept a little bit back when we were looking at those like elevator problems. And remember how we had, what does your weight feel like when the elevator is accelerating up, and what does it feel like when the elevator is accelerating down? And when the elevator was accelerating down, it was moving out from underneath you, right? And so you felt like you didn't weigh as much. And then we talked about, what if it was accelerating at the acceleration due to gravity? What if the floor was falling at 9.81 meters per second squared, but then you were also falling at 9.81. So you're just hovering above the ground. There's no normal force pushing back up on you. That's what weightlessness is. It doesn't mean that you don't have mass, and you still have a force due to gravity. You just don't have a normal force pushing back up on you so that you register that. So what's actually happening with these astronauts out in the space station where they feel like they're weightless, that's it's not true like weightlessness, meaning that there's no forces of gravity acting on them. They're just falling at the same rate as the Earth is moving out from underneath them. And it goes back to that orbiting idea. So that's why they feel weightless. They're not getting any closer or further away from the Earth. Now, our last concept here for acceleration due to gravity is Einstein's idea behind it. And here's what's amazing and interesting is if I were to ask you, what is gravity? You might say, well, when I drop something, it falls towards the Earth. Or it's an interaction between items that have mass. But what causes that interaction? Like, what is the purpose, not purpose, what is the reason behind gravity? Why do things fall towards the Earth? Why do things that have mass have an interaction between them? We don't have an answer, but we have some theories and we have some thoughts about this. And Einstein's theory of gravity was that we have space itself being manipulated or curved by anything that has a mass. But this is in like a 3-dimensional space instead of a 2-dimensional space. So like, I really like these image. Think of it as like we're holding a blanket and we're holding it all, like a whole bunch of us are on the edge of the blanket. We're holding onto it really tight. And we put a tennis ball in on the blanket. It makes a little indent, right? And then if we take a marble, we put that on the blanket, it would also indent and it kind of falls towards the tennis ball. And then if we put something really massive like a bowling ball, then it makes this big indent and everything kind of like falls into that. So that was his idea that, instead of a piece of fabric, it's space and time itself that's being curved and manipulated, and that is what causes gravity. And one justification behind this, or pieces of evidence to support this, is the idea that black holes, so gravity is so great, space becomes bent back onto the object, so no light ever escapes. That gravity of the black hole causes light to curve around these black holes, and we've seen that. So interesting thought there with gravity. And then now we're just on to our practice problems. Let's see where we're at time-wise. Yeah, let's look at a couple of these. So, what is the gravitational force between two 15-kilogram packages that are 35 centimeters apart? Okay, so we have mass 1 and mass 2. They're both 15 kilograms. And then they're 35 centimeters apart. Let's put this in meters. So R is going to be 0.35 meters. And we want to know what that force due to gravity is. Okay. Well, that base equation, and let's write down our constant as well. This G constant, 6.67 times 10 to the negative 11, and units are Newton meters squared per kilogram squared. Okay. So let's use this equation. Force due to gravity is equal to G multiplied by M1, M2 over R squared. Okay. So we know what G is. I'm just going to write G for now instead of writing the big long number. And then we have M1, 15 kilograms, M2, 15 kilograms, divided by R, which is 0.35 meters squared. Okay, so we have, and I guess I'll show you how I plug this in. So I'm going to take G, 6.67 times by 10 to the negative 11th. Anytime I have something in scientific notation, I like to put it in parentheses, saying treat this all as one number, one unit. And when we're multiplying that by this whole thing, the top of it is mass 1 times by mass 2. Okay, and then the bottom is 0.35 squared. And now I really love this calculator because it gives you pretty print, and so it shows that like I have this multiplied by those things. It's set up in the way that I want it to be. So I get force due to gravity of 1.2251. Let's see, 3 sig figs, 2 sig figs, 2 sig figs. So 1.2 times 10 to the negative 7. Wow, that's tiny. Negative 7, and it's a force, so that's in newtons. Okay. And see, that's something that's I really like seeing, is anything that has gravity. Like, I have mass, so I have gravity. This pen has mass, so it has gravity. So there's actually gravitational attraction between me and the pen. That if it was just me and the pen floating out in space with nothing else around us, we would slowly come together because of gravity. But gravity, in general, it's a weak force, and we have to have something really massive in order to cause any kind of like substantial, noticeable force. And so 2 items at 15 kilograms, in the comparison to like a planet, it's relatively small mass. So it's an extremely small force. Let's do a unit analysis, because we said newtons, but do we in fact actually end with units of newtons? Yeah, we have time for that. So G is a newton meter squared per kilogram squared, and I'm multiplying that by, so this is G, I'm multiplying it by M1, M2, so it's kilograms, kilograms, so that would be kilograms squared. And then R is a distance, which is meters, and it's squared. So meters squared. So this cancels with that cancels with that, and I end with the units of newtons. Okay, so that checks off. Okay, so I think we're going to skip number 2 if we have time, and I'm feeling confident with where you guys are at with this stuff. Maybe I'll come back and do number 2 with you. But let's move on to number 3 and maybe number 4. Okay, so that's what the last video will be. We'll just kind of wrap up the practice problems that we're working with.